Hello, Polar Posse. Can I call you that? I hope so because I just did. Today we're going to be starting on page 3 of the Polar Packet, even though I'm turned to page 2 because I want to recap what we did in the last lesson. But I could not be more excited for the converting questions that we get to today. I think these are going to blow your mind, and this unit just gets better and better as it goes. So the question of the day is, why was Cinderella bad at soccer? Guys, she was always running away from the ball. So that's why. Just to reiterate, the big facts we went over from yesterday, none of this is new news to us. It's nothing to memorize for the first time ever. If you know the definitions of sine and cosine, you're going to be A-OK when you want to find x and y given r and theta. If you want to find r and theta given x and y, you want to go rectangular to polar. Think of Pythagorean theorem to get r, and think of the definition of tangent. We'll keep coming back to that to get theta. All right, so now the main event. The questions we left off on page 3, the first two I want to look at are 15 and 16, converting to polar form. Now would be a good time to take a timeout on the video, and if you haven't already, get your own look at 15 and 16 and see what you could do creatively to get x and y out of there and r and theta in there. Okay, so when you come back, we'll time in and we can look at 15 together. All right, what'd you decide to do? For 15, you want to get rid of y and x. One quick way to do it might be to just sub in for those facts about r sine and r cos theta. So for r sine theta, we could plug that in for y, wherever we see y. And then we're allowed to plug in r cos theta is one strategy for wherever we see x. And this has successfully gotten the equation into polar form. I see no more x's and y's. I only see r's and thetas. We'd like to clean it up a bit. It says we're manageable. If we could get r by itself, that would be good. And it isn't too bad to do that here. So we don't need the parentheses. R sine of theta equals 2 r cosine of theta minus 1. It would be nice to have the r's on the same side, right? So that we could consolidate. R sine of theta minus 2 r cosine of theta equals negative 1. And then let's get r by itself. Let's pull it out as a GCF. Sine of theta minus 2 cosine of theta equals negative 1. And we call this final answer negative 1 over the difference, sine of theta minus 2 cosine of theta. So here's one case where I don't think anybody would argue with me on this. Your original equation of just like a line, the line y equals 2x minus 1, a lot simpler in rectangular form than it comes out to be this whole thing with trig functions in polar form, but this would still give you that equation, that diagonal line. All right, what about this one? I should ask you the question first. What are you expecting to come out as a graph? This is our first parabola that we want to convert into polar form. So we have x and y. Let's get this in terms of r and theta. And I'll put parabola, since we know what shape it is. Always good to keep that in mind. Where we see a y, we can plug in r sine theta. That's what we did last time. And when we see an x, we can do the same, but I'll have this being squared. So instead of x being squared, it can be r cosine of theta squared. Now it's time to just tidy it up where we can solve for r. Now you have r's on both sides of this equation, and in a couple examples we've already seen, it's actually okay to square both things here and then reduce both sides by a power of r. So we can cancel one of the r's on the right-hand side and both r's on the left. You get sine of theta equals r cos squared theta. It's already looking a good bit simpler. And then we can get r by itself. So it'd be sine of theta over cosine squared is one way to write it with r solved for in polar form. Another way to write it is for you to split these trig functions up, right? You have a 1 over cosine theta and you have a sine over cosine theta. So this is also known as r equals secant of theta times sine over cosine. Remember the quotient identity? Tangent of theta. So two different versions that are both great. They're all polar, they're solved for r, and we use those same facts that we were using to convert points. All right, some good ones at the bottom. Actually, only one left. We kind of got carried away in the last lesson. Let's look at number 20. 20 is a great one. So for 20, I don't think we'll know what shape this is going to be until all said and done. When we see this in rectangular form, I think it'll be a little bit easier to pick it out. But all it says right now is r equals 6 sine of theta. And we're interested in getting this in terms of x and or y. We're going to pull a trick here that you are allowed to do. Remember a couple times, remember in the last problem where I said you can divide both sides by r, and that's okay. You're dividing by the same exact quantity. We can also, it might be nice, it actually might kill two birds with one stone if we actually get an r, another factor of r on both sides. I'm going to actually try this by multiplying the quantity on both sides of the equal sign by r. It gives you an r squared on the left, which is great because we know an expression for x and y in terms of that. And it squeezes an r into the right-hand side, which makes for also a very convenient substitution, right? For r squared, we know we can sub in by Pythagorean theorem, x squared plus y squared. On the other side, because we introduced that r, we get to just plug in a y. And here's your answer in rectangular form. We can move everything to one side, right, and have this in general form. X squared plus y squared plus or minus, I should say, 6y equals 0. So this is your equation of a what conic section? Not a parabola this time. Both are squared, same coefficient, a circle. And if for fun, I asked you to go a little further and tell me really what are the features of this circle, where is it centered, and what is its radius, well, we could get this into standard form. It's been a little while. Y squared minus 6y, we got to complete the square once in this case. So we could add half of b squared, so half of negative 6 is negative 3 squared, add a 9 on both sides. You get x squared plus, now factored, y minus 3 squared equals 9. And this is a circle centered where? Centered at 0, 3, up 1, 2, 3. And the radius is going to be 3 as well. So you're up 3, down 3, left 3, and right 3. This is a circle that's just kind of sitting on the x-axis, center up at 0, 3. Nice work. All right, so this is where it gets really good as you turn to page 5. I want to skip down to, hopefully we have enough time to look at all 4 of these. Check out this first one. I have no clue what this is going to look like because even in this rectangular form, it's not a conic section that I'm feeling very comfortable with yet. Maybe this is finally a case where we can take something that's more complicated rectangularly and get a simpler, easy to handle equation in polar form. I cannot wait. Okay, let's go left to right and see what jumps out at us as kind of good strategies and ways we can make this thing look simpler. On the left, what do we have? Ooh, an x squared plus y squared. That's a dead giveaway. I'm going to put an r squared in for that on my quest to getting rid of as many x's and y's as possible and getting subbed in as many r's and thetas. On the other side, it's not so quick because it's not like you could just sub in something quick in terms of r for both parts. So I'm going to actually work on each part separately. I know that for any x I see, I'm allowed to plug in an r cos theta. So that's what I want to do for this first x, and that's squared. Similarly for y, in parentheses, can you plug in r sine of theta? And that's squared, like that. So this gives you r to the 4th equals r squared cosine squared theta minus r squared sine squared theta. We have successfully gotten this into polar form. Now it's like the touch-ups. We're going to try to make it look aesthetically pleasing. I see a couple powers of r in every single term, and I want to reduce everything by r squared. So I'm going to divide the expression that's on the left by r squared. I'm going to divide each one of these guys by an r squared once my cursor comes back up again. So by r squared and r squared, every single term of this. See how that goes. Okay, let me write this a little bit neater. So you've got r squared, that's r to the 4th over r squared. You have these canceling, cosine squared theta, minus these canceling, sine squared theta. And I mentioned something about this thing getting to look really simple by the end of it. I like the way it looks. This is sufficient, but I'm wondering if a little voice is calling to you. Is there a little voice whispering to you like, hey, it's me. It's your old friend. I'm a trig identity. Change me. I'm a double angle identity. It is. Can you mark this here? This is one of your old trusty double angle identities. I bet if we were together, I would hear like the aha and oh yeah, I can't wait to use the identities again. Hopefully I wouldn't hear groans and like, oh man, those again, but it will make this a good bit simpler. All joking aside, you can write this as r squared equals. Now we have to remember which double angle identity this was. This one was cosine of 2 theta that had 3 convenient versions. A nice, succinct expression that you could graph polarly, we'll get to that, and that's in polar form. Because, spoiler alert, the double angle identities are going to come up in this worksheet and in this homework, we might as well list them up above to jog our memory. Write down, you can pause the video and write down what you remember or write them with me. Sine of 2 theta had one version. Expect it to come up in one of the problems coming up soon. 2 sine of theta, cosine of theta was the one version. Cosine of 2 theta had 3 versions. If you just know one of the 3, like if you know this first one, you'll know the other 2 by subbing in with other identities. So cosine of 2 theta, one version of it we just used, cosine squared theta minus sine squared theta. You could also sub in, according to the Pythagorean identities, to get it all in terms of sine squared or all in terms of cosine squared. So a second version was 2 cosine squared theta minus 1 was also equivalent. And the third version was 1 minus 2 sine squared theta. So 3 versions of that cosine of 2 theta identity. Tangent of 2 theta, you're not going to see this a ton. We might as well put it in the list, but you won't see it a ton in these conversion problems. If it comes up, we'll be ready for it though. 2 tangent of theta over 1 minus tangent squared theta. Oh, consider yourself warned, right? These double angle identities, we've known about them, we've used them. They're out there and they might be useful. I think this means we're ready to tackle 2, 3, and 4. So go ahead, keep this stuff in mind. I see a polar equation, have no clue what it's going to look like on a graph. Maybe once we convert it to rectangular form, we'll have a better idea. What are you going to do? So one thing that would be cool, this is just a lonely r sitting here. And there definitely is a way to write that in terms of x and y using Pythagorean theorem, but it actually might be nice as a step 1 to get rid of the fraction, to multiply that denominator over to the other side. Because if you bring the r into both parts, you'll have this convenient r sine of theta, where nicely a y could just slide right into that slot. So it actually makes this part of the converting a little bit easier. So step 1, let's get rid of the fraction. Step 2, now you have no choice. Now you got to start plugging in. You have an easy job here and maybe a tougher job there. What can you write for just plain old r? Well, if it were r squared, you could write x squared plus y squared, right? If I square root that Pythagorean theorem expression, I get positive or negative the square root of x squared plus y squared. That's what plain old r is going to look like. Plus, we're still converting. We can write a y. This was the part I was excited about, just writing a y for r sine of theta equaling 2. This looks pretty good. You could actually leave it this way because this one's not as convenient to solve for y, but we got to do better than that. I don't want to leave it this way. What if the extra directions were, tell me what this graph looks like? Would you believe that this is actually a conic section in disguise? It's one of our 4 classics, circle, parabola, ellipse, or hyperbola. Let's find out which one. Well, we want to get rid of that square root. It might be nice to isolate it first. So we'll leave this so it's by itself. And we get a negative y plus 2 on the other side. Now we want to carefully square both sides, right? And that should get rid of the plus or minus sign. And we do have to remember to FOIL on the right-hand side. Okay, so we get just x squared plus y squared on the left. On the right, you have the first term squared plus double the product, so minus 4y, and then the last term squared plus 4. This, is it looking circle-like? Well, I guess not when we subtract a y squared from both sides. I think we've solved the mystery, and this turns out to be a parabola. If we're interested in seeing this in standard form, one quick GCF gets us there. So a negative 4 taken out, and you have y minus 1. This is something that we can easily graph now. It's great review for us. Its vertex is at 0, 1. So up at 0, 1. If we think about which way it opens, x is squared with a negative p-value, so we know it's going to open down. And 4p equals negative 4. That means p equals negative 1. You would be going down 1 unit to the origin to get to the focus. And that's a little rough sketch of what that graph is. So I'd say this is an equation that's simpler in rectangular form. Okay, we're saving 3 and 4, saving the best 2 for last. So tune into the next part of the segment and we'll try to get those converted. Okay, until then.